Alors, il me fait grand plaisir de vous présenter professeur Paula Lago. Paula vient de l'Université Concordia, de mon université. C'est une nouvelle chercheure en émergence au CRIUGM. C'est une ingénieure qui est professeure au département de génie électrique et génie computationnel logiciel à l'Université Concordia. Et sa spécialité est dans l'analyse des données des technologies portables. Alors, nous avons maintenant vraiment une recrudescence, une quantité toujours grandissante d'objets connectés qui vont mesurer les mouvements qu'on fait, nos comportements. Et puis la grande question, c'est comment est-ce qu'on gère cette quantité massive en fait de données et comment est-ce qu'on peut extraire des patrons qui nous aident à intervenir, à détecter des changements et intervenir auprès des patients dans ce contexte-ci. Donc, les travaux du professeur Lago sont très importants pour développer les technologies, les modes d'analyse pour l'utilisation optimale de objets, de ces technologies portables. Alors, c'est avec grand plaisir que je vous présente professeur Lago.
Bonjour à tous et à toutes. Je suis très contente d'être ici avec vous. Je m'excuse. Je vais continuer en anglais. Merci Philippe pour la très belle présentation. Um, as Jean-Philippe was saying, I work with wearable sensors and wearable computing. And as you know, these sensors provide us with continuous measurements of physical and of behavior, physical behavior, physiological measures, but they are often said to be data rich but information poor because they fail to provide us with actionable insights of how to improve our health or how to improve treatments to make them more effective. However, ideally, we would like this data, these continuous measurements, this multimodal information to help us build personal models of health and, for example, predict diseases before symptoms appear and personalize treatments so that they can be more effective to every person. So instead of doing population-based models, that we can really do personal models. However, there are still a lot of challenges to make this vision a reality. Today, I want to briefly talk about machine learning and its role in wearable data, wearable sensor data analysis, and illustrate two challenges that we have when working with this data. The first one is the variability that exists in real world for these sensors. And the second is about modeling long-term patterns. So once we have months of years of data, how do we turn that into insights? So just to briefly explain machine learning and its role in wearable data analysis. It is a subset of artificial intelligence that uses statistical methods to enable machines to learn from data. So instead of us trying to tell the machine what is the model or what are the patterns to look for, we would like the machine to identify those patterns and give us insights from the data. It involves creating algorithms to identify patterns and make prediction. Yeah, instead of programming step by step, we program how to identify the patterns from the data. And because we have a wealth of data from wearable sensors, it's really suitable for machine learning and artificial intelligence to learn from this data. There are 3 different flavors of machine learning. One is supervised learning, where you have examples of data and an answer for each example. So for example, if we have movement data and we want to predict if a person will have a cardiovascular disease, if that's relevant, or if we have the ECG data and want to predict if there is any anomaly in it, and unsupervised, where we have only data but no answer. So in the first one, we would know if this data corresponds to disease or not, and in the second, we don't really know. So for example, if we have daily movement data and we want to know if this is an abnormal behavior for that person. The main concern is that these both involve having past data to learn from, and they both assume that the future data will look like the data from the past. So that's the main challenge in real life settings, that assumption that the future data will be similar, because we have, in real life settings, we have high variability as we are not controlling the setting. So for example, there are many different types of wearables that can be used in different parts of the body. We have smartwatches, which can be used in the left or right wrist, or we have earbuds, which will be worn in the ears, or we would have a phone, which can be in the pocket or any other place of the body. And there is a lot of individual variability. And what has been seen is that this often leads to non-generalizable results. So we do a study. In the study, we have great prediction accuracy. Just from wearable data, we can predict if the person has anxiety, or we can predict if the person has cardiovascular disease. But once we take it out of the study and want to study a different population with a different device, these results do not generalize well. And the second challenge is modeling a multiple temporal pattern. So how much data do we consider? Do we keep only the last short-term pattern, or do we need years of data, and how to model those, and the importance of, like, let's say, your lifetime versus your recent past. So first example that I have is about activity recognition under variability settings. So in this study, we are concerned with identifying between two very simple activities, walking and not walking, cooking in our case. And we use supervised machine learning for this. That means we collected training data, and we know for each of the activities, like this, we used accelerometers for this. So we know this accelerometer data corresponds to which activities. And we used a classification model to classify the activity. And our goal was to assess if deep learning models, which are also learning from data, would perform well in real world conditions where both the device and the position may be changing. So it may happen that different, like one person has a Apple Watch and the other has a Fitbit. Like, can we train a model that uses either of those? Or one person wears their device in the right hand and the other in the left hand. Like, will our models support that? So we collected data from 16 participants, diverse age ranges and diverse population. We collected data with two different devices. One is called BlueSense and the other is Empatica smartwatches. And we used the sensors in various different positions. So right hand, left hand, and well, we also studied the orientation, like what happens if the sensor rotates a little. And we train the models in two different settings. The baseline is we train the model, let's say with the same device, with one device, and then evaluate the performance of the model in recognizing the activities using the same device, same position, same orientation. So nothing changes. We did this very controlled in the laboratory. And the second setting, which is the variability setting, is we train, let's say, with the empatica on the left hand. We evaluate with the BlueSense device. Okay, so, and here we keep the testing data equal, not the training data, just to avoid the effect of the evaluation being perhaps harder in one setting than the other. So the test is the same for both models, as the training data that's changing. And we use, here is the device. Here we're changing the device. We use 3 different types of models. This is called Attend and Discriminate. This is called DeepConv LSTM, and this is called Tiny Human Activity Recognition. The differences between them is, let's say, how big the model is. So how much data are they taking on, how many patterns are they trying to learn, or yes, like different, let's say, different types of patterns they are attending to. And in all 3 different models, as you can see, we are here evaluating how accurate the recognition of the activity is, so if they can recognize the activity well or not. So in all 3 models, we had a very significant drop in performance, meaning that if we had this model in real life and the person just changes the device, the model would not show the same accuracy. And we have the same effect if the position changes. So here we are testing with right hand and left hand, same device at different positions. So we also see the drop in performance in all 3 models. And this is due to the difference in the distribution of the data, which we measure, with a metric called MMD, which is measuring how similar the distributions of the test data and the training data are. So if this MMD is high, it means the train and test are not very similar. And if it's low, it means the train and test are similar. So we can see that for the baseline where nothing changes, the distribution differences are lower than when there is a variability in the evaluation. So what this tells us is that the variability in subject, devices, and position, the change in device can affect, for example, the sensitivity of the sensor, the sampling rates, how many samples we have per second, per minute. The position affect the performance in this case of activity recognition models, but it can also be the performance of, let's say, disease prediction models. So for now, in this context, the recommendations are to use the same device or firmware for the entire experiment. It often happens that the software of the wearable device will change, so the measurements that it is taken can change a little bit, and that can change the prediction of models. Teach a participant how to correctly wear the device. And in our case, we would prefer smaller models because they cost less, and all of the models were having the same drop in performance. So we didn't see any benefit in having larger models. And of course, we were having a few participants. So we need to test with more data in the future. The second challenge that I want to illustrate is modeling long-term patterns, which we want to use to create personal baselines. So it is often said that what matters most is the change instead of what your current state is. So was there a change in your behavior lately? Are you sleeping more? Are you moving less, having less physical activity, less social contact? So longitudinal patterns and creating personal baselines enable reasoning about this. Like if this activity happened, was that an unexpected occurrence of the activity or is it something abnormal? Was this activity, or on the other hand, did the activity occur when expected? So we expected the person to eat because it's lunchtime, but that didn't happen. So is that normal or abnormal? Does it mean anything? Did the activity take longer or shorter than usual? But to reason about this, we need to create a personal baseline. We have been exploring two different models to create these personal baselines. One is based on routines and the other is based on rhythms. Both models have been extensively used in literature. We want to study them in the context of wearable data. I will explain the challenges. So routines are consider the sequence of frequently occurring events. So the person usually, let's say, sleeps, then cooks, then eats, and then goes to work, and so on. Like that's your personal routine. One of the challenges in identifying routines is that we assume we have previously identified events, for example, activities, and we've just seen how difficult it may be in real life settings. For this, we used unsupervised learning, meaning we don't have any answer for this. We do not really know what's the routine of the person unless we ask. And if we are using sensors to get a more objective measurement, but rely on subjective report to measure it, it's difficult to evaluate. But we can, let's say, model a routine or a typical day of a person. And what we've been exploring is how do we contextualize these activities so that the sequence is not a typical day, but also, let's say, a typical Saturday, a typical Sunday, or what happens if the weather changes, does the routine change? We're still exploring, so I don't have the results yet, but I have the challenges of what happens when we try to do this. And the second model that we are studying right now is based on rhythms, which focuses not on identifying each event, but on learning the periodicity of the measurements. This is typically related to circadian rhythms, but we want to study various rhythms, not only daily rhythms, but also their weekly or monthly rhythms, so that your behavior changes according to different temporal granularities, let's say. And this is often used with the regression, but again, the main difficulty is how to evaluate if the model is correct or not. And then we have lots of challenges when trying to just take all the data and create a baseline for one person. The first one is if we are having data that is collected very frequently, multiple measurements per second, multiple measurements or per minute. Usually the first step is to aggregate the data in smaller segments, but there is no standard in how to do this. So some people will use 5 minutes, some people will use 1 hour, some people will use 6 hours, and the results will be very different in of these strategies. So we want to study which one works best, or if we really need different for different contexts. The second is context dependence, because differentiating abnormal changes from contextual changes. It is a change because there is a weekend, because it's raining, because there are visitors, or is this really something that we should worry about? And the personal differences, so we need to balance the need of collecting more personal data with really taking advantage of having data from multiple people. And like I said, the data heterogeneity, changes in devices, form factors, individuals, and changes through time that make it difficult to maintain a personal profile over a long time. Because once we learn from a very long time, it is harder for the model to recognize recent, let's say, recent routines. It will, we say the weight of history is too much. So how to manage these changes, it's what we are studying. In our laboratory, we are creating tools. For example, we've already created a platform to integrate data from various wearable sensors. We can integrate data from Fitbit, from Empatica, and from the BlueSense, which is a custom device for now, but we are looking to integrate more wearable sensors in this. And we are particularly interested in raw data for now. And we are looking for collaborators for data collection or sharing in order to validate our algorithms. So if you are interested, please contact me, and I will be happy to give you.
Des questions pour professeur Lago.
Thank you for the question. Here we used windows based on the sampling rate. We used 150 samples. So because of the change in sampling rates, that would mean either a second and a half or 2 seconds, and depending on the device. And we used a short window because the activities were walking or non-walking, and a short window has been shown to work well on periodic activities. So we thought that the short window would very help us to identify the walking and not walking. In terms of the features, because we are using deep learning models, which are supposed to learn the features by themselves. We are using the time series in it. We previously filtered the time series to remove very large noises, to mainly to remove large noises, and also if we were training, for example, with Empatica, which has a low sampling rate, we would then downsample the blue sense to make it consistent. And on the other hand, we would upsample the Empatica data. So in this case, we were using the time series directly. Thank you.
Thank you, Paula, for a very nice presentation. The thing that struck me most was that usually when you talk with people who don't know anything about that, they say, oh, let's use objective measures with wearables. And what I learned from your talk is that it's not that simple. And there's, in fact, a lot of complexity. And it's not true that it is, it's going to provide something maybe more objective and easier to interpret than questionnaires, because we often use subjective questionnaires, right? So I like this view because it really gets deeper into the process of interpreting these data. And also I would like to stress also that by definition, I suppose wearables are always longitudinal, because you see that you're never doing something once. You want to see things over a period of time. So yeah, thank you. That was more common, but if you have something to answer to that, that would be great.
Yes, thank you for the comment. Yeah, that's also true. I have two reactions, let's say. The first one is that yes, we have all the complexities. They can also provide some useful information. So if you use always the same device and the person is really wearing it at least consistently, the steps are not, let's say, accurate to the one step, but the trend is something that we can say it's accurate. Detecting activities is more difficult. So we always rely on the participant telling us what's the activity, which can be cumbersome still. So that's why we're developing algorithms to improve this. And my second reaction is that it's supposed to be always longitudinal, that at least, let's say, in the engineering studies where we are not a doctor with authority, right? Because if your doctor tells you wear this device because it will help you, you'll probably wear it more consistently. When we tell the person wear this device, they wear it half of a day, the other half they don't, then they wear it for 3 days, during the weekend they forget. So that's the other challenge that we have, how to still obtain some insight even when the data is broken like this.
Hi, Paula. Thank you very much for your presentation. I have a very brief 2 questions. The first one is about the raw access, the access of the raw data. Because if you are using Apple Watch or Fitbit, sometimes the algorithms that they are doing themselves, so you did not know what they are capturing. So how did you counteract that? And mostly because even with actigraphy or this kind of actipol, even the unit that they use to interpret the physical activity is not the same. So my question is how you are counteracting that. That is my first question. And my second question is about what Sylvie asked you is, and what is sometimes I say to my student is not because they are reporting data that they are real, because for example, if you look at the longitudinal Canadian study, all the participants are physically active based on the wearables that they are doing. So I don't know who, but in my opinion, doing more than 200 moderate physical activity every per week when you are 82 years old in average. It's quite crazy for me when I'm a kinesiologist. So do you have this kind of how we can correct or even train researcher or people that they are doing this data to be more careful about how they are interpreting? So using the software of the brand versus air model or this kind of stuff that they are correcting for this kind of artifact.
So how we are, let's say, what we are using right now, we are using two devices. One is Empatica, the other one is Fitbit. Empatica does provide both the raw data and their, let's say, metrics like the steps, the heart rate. So we can really compare and take a look at the raw data and see if our models would predict the same or not. That's a little bit, at least reassuring in one way. For the Fitbit, there is no access to raw data. Like it's always the steps or heart rate, and they do correct, for example, the calories and the heart rate. It's never zero. There's always a value, even if the watch was left in the drawer. So right now, we've been doing two things. One is first wearing it ourselves just to be aware of this. So I always do my students, they have to wear it first and check out their data, and they realize all of these problems. Like I didn't wear it and it still says I have this heart rate, and it still says I have this. For the steps, it's usually more accurate, like you have 0, 0, 0. We've been trying to work on a detection that it's not being worn. So if it's very still, let's say that, but it's very not accurate at the beginning. So with Fitbit, they're still exploring, and what we've been mostly working with is their rhythm. So even if there is no data, can we have at least a rhythm on the activity, or mostly on the activity, or on the sleep, but mostly on the activity. But I don't have, that's what we've been working with, and so far we prefer the raw data, at least for our models.